So what is a major product of the reaction of nitrobenzene with one equivalent of bromine and iron 3 bromide? Well, if I look at nitrobenzene, the nitro group is a meta-director. So I'm going to look for meta-direction. Now, if I look, this is para, this is meta, that's ortho, ortho and para, and meta. So if I look, it's either going to be this one or this one based on meta-direction. It says one equivalent. Since in the reaction, one bromine adds one bromine to the ring and makes one hydrobromic acid, this is only going to do a single bromination. Not only that, bromine is a deactivator, so the second reaction will be slower than the first addition of bromine. So the correct product for this reaction is metabromo-nitrobenzene. So which of the following compounds would react fastest with nitric acid in sulfuric acid? Well, if we look at this, this is going to add a nitro group, and it doesn't really matter what the reagent is because how fast it reacts doesn't depend on the electrophilic reagent. It depends on what are the substituents. So if I look at the substituents, you can see that we have nitro group, a toluene group, a bromo group, a methoxy group, and a carboxylic acid group. The carboxylic acid and nitro group are meta deactivators, so we can automatically throw those out. They're very slow. Bromine is an orthopara deactivator, so it's also deactivating and slower. Both the methyl group and the methoxy group are activating. Which one is a stronger activating group? The one with the non-bonding pairs that are directly adjacent to the benzene ring are the greatest activators. So the compound that would be fastest would be anisole because it has oxygen attached directly to the ring. So what would be the main product of nitration of benzenesulfonic acid? Well, if I look at benzenesulfonic acid, it's got the sulfonic acid group on it, which is a meta-director. So the nitration is going to occur on the meta position. So it's going to be meta-nitrobenzenesulfonic acid. So which one of these statements is not a limitation of Friedel-Crafts alkylations? Okay, let's go through them one by one. Can carbocation rearrangements occur? If it's primary, you're going to see that. So this is a limitation. Can polyalkylation occur? Yes, because as you add an alkyl group, it becomes more activated, and polyalkylation is really common. Substrates that have activating groups, only substrates with activating groups can be used. That is true. Electron withdrawing substrates that are deactivating will not allow Friedel-Crafts to occur. Vinyl halides cannot be used. Well, that's very true. It must be an sp3 carbon halide to participate in a Friedel-Crafts alkylation. The halogen in the aluminum halide must match the one in the alkyl halide. Since the halide's a leaving group, it doesn't matter what it is. So the halogen can be anything you want it to be. So this is not a limitation. Which of the following is not used to do electrophilic substitution? Really, all you need to know is what conditions have you used to do any kind of electrophilic substitution. This does nitration. This, well, chlorine, this is a catalyst, but here I have bromide, here I have chlorine. I would expect to see a mix-up of the chlorine and bromine. I would want iron 3 chloride here instead. Here I have iodine and copper 2 chloride. That will give us iodination of the ring. These are the conditions to make the sulfonic acid. And here is a Friedel-Crafts acylation. The only one that doesn't look right is this one. Arrange these in order of decreasing rate of chlorination. Well, if I look at these structures, I will see I have an activator, and a deactivator. So this is last. Why is this an activator? You say, I see a carbonyl, but watch. You see how the nitrogen is directly on the ring, so that makes it an activator? So is this oxygen. That carbonyl is one away, so it is not a deactivator. Which is more activating? Well, because oxygen is more electronegative than nitrogen, the nitrogen is more activating than the oxygen. So the order is 1, 2, 3. So which compound will react fastest with bromine and iron 3 bromide? Well, we don't even have to worry about that as bromine and iron 3 bromide. For any electrophilic addition reaction, the one that reacts fastest is going to be the same here. If I look at these compounds, I can see that this is an orthopara director and an activator. This is an orthopara deactivator. This is a very electron withdrawing group. It is not an activator. It would have to be hydrogens here for it to be an activator. This is a deactivator. And this, because it has a carbonyl here, is a deactivator. So the fastest is So which one of these compounds will add a nitro group to the meta position? Well, all of these groups can be classified. Nitrogen on the ring is an orthopara activator, so this goes orthopara. Chlorine and fluorine are both orthopara deactivators, so these go ortho or para and not meta. And this is a deactivator, and it's a meta-directing deactivator. So the compound that does meta-direct. Which reagents would best change benzene to propylbenzene? Well, to add an alkyl group to a benzene, we need to have a Friedel-Crafts reaction of some sort. If I look at the first reaction, there's aluminum chloride, but there's no chlorine attached to this that it can pull off. So this is not Friedel-Crafts. If I look at the next one, this is Friedel-Crafts alkylation. But the problem with this is that not only would you have multiple alkylation, but you would have mostly rearrangement to the secondary carbocation before addition. If I look at the bottom one, there's no chlorine on this to be abstracted by the aluminum chloride, so this will not add anything to the ring. C is a Friedel-Crafts acylation. It would easily add to the ring and only once, and then if you follow it with hydrogen and palladium, you would get reduction just to the propyl group. So this is okay. Which one of these compounds will not undergo a Friedel-Crafts acylation? Well, if I look at the compounds, you can see that we have an activator, and we have a deactivator here, but it's not one that's so deactivating that it won't do a Friedel-Crafts acylation. This actually will go. But this one has 3 fluorines on a carbon. This is as electron withdrawing as a nitro group and would not allow Friedel-Crafts acylation to go ahead. So that is the correct answer. Which substituent is deactivating and orthopara-directing? Well, this has a double bond to an oxygen on the carbon that would be attached to the ring. So this is deactivating and meta-directing. This has a nitrogen with non-bonding pairs here directly attached to the ring. So this would be activating an orthopara. The sulfur is going to be a mild activator with its non-bonding pairs. It would be a poor activator because the non-bonding pairs aren't going to overlap well with the pi system. But it's not a deactivator. What is this? This is deactivating and it's an orthopara director. So the correct answer is A. Which of the following is the least deactivating substituent in electrophilic aromatic substitution? Well, this is a heavy deactivator because it's got a double bond to a nitrogen adjacent to the ring. This would have a double bond to an oxygen adjacent to the ring. This has a nitrogen adjacent to the ring, and the double bond is to the oxygen is 1 carbon away. So this would not be a deactivator. It actually would be an activator. Here you have a highly deactivating substituent because you have 2 oxygens double bonded to a sulfur. So the correct answer is this is least deactivating. In fact, it's an activator, not a deactivator.